When inspecting an automatic transfer switch, the spacing between terminal lugs on the load and normal power sides is crucial for electrical safety and code compliance. The National Electrical Code, or NEC, provides guidelines for this spacing, and referring to a relevant table such as Table 408.56 in the NEC 2005 is a good starting point. However, it's important to understand the scope and applicability of that specific table within the context of the entire NEC. Table 408.56 addresses minimum spacing between bare metal parts of opposite polarity or between bare metal parts and ground. It's important to confirm this is the correct table for the specific situation. Several factors determine the required spacing. Firstly, the voltage level is a primary consideration. Higher voltages necessitate greater spacing to prevent arcing and short circuits. Secondly, the environmental conditions can impact spacing requirements. For example, damp or corrosive environments may require increased spacing or additional insulation. Thirdly, the specific type of equipment and its listing standards can also dictate spacing requirements. Automatic transfer switches often have their own specific listing requirements that may supersede the general rules in the NEC. When evaluating the existing installation, the use of unlisted rubber as insulation between terminal lugs is a significant concern. Non-listed materials may not provide adequate insulation and could pose a fire or electrical hazard. It is vital to replace any non-listed insulation with materials that are specifically listed and approved for electrical insulation purposes and appropriate for the voltage and temperature rating of the application. Regarding opposite polarity, this generally refers to different phases in a polyphase system or the hot and neutral conductors in a single-phase system. The NEC specifies minimum spacing between these conductors to prevent faults. The distance outlined in Table 408.56 depends on the voltage. The proper approach involves firstly, identifying the voltage level of the system. Secondly, consulting the appropriate table in the NEC, which could be 408.56 for another relevant table depending on the specific installation. Thirdly, verifying that any insulation materials used are listed and approved for the intended application. Fourthly, ensuring that the installation complies with all applicable local codes and regulations, as these may have additional requirements beyond the NEC. If there is any doubt about the correct spacing or insulation methods, consult a qualified electrical engineer or inspector. They can assess the specific installation and provide guidance on ensuring compliance with all applicable codes and standards. It's also critical to remember that electrical work can be dangerous, and only qualified personnel should perform installations or repairs. The NEC is not a design manual, but a set of minimum safety standards. Good engineering practice may dictate spacing greater than the minimum specified in the NEC. It's always better to err on the side of caution when it comes to electrical safety. The goal is to create a safe and reliable electrical system that protects people and property. When evaluating terminal lug spacing, consider the following. Firstly, the voltage rating of the equipment. Secondly, the ampacity of the conductors. Thirdly, the operating temperature. Fourthly, the environmental conditions. Fifthly, the manufacturer's recommendations. Sixthly, the relevant NEC articles. Seventhly, any applicable local codes. By carefully considering these factors, you can ensure that the installation meets all applicable requirements and provides a safe and reliable electrical system. Remember that electrical codes and standards are constantly evolving, so it's important to stay up to date on the latest requirements. Regularly reviewing the NEC and other relevant publications can help ensure that you are always following best practices. Additional considerations include the type of conductors used, the method of termination, and the presence of any potential hazards such as moisture or corrosive substances. Properly torquing the terminal lugs is also essential for ensuring a reliable connection and preventing overheating. Use a calibrated torque wrench to tighten the lugs to the manufacturer's specifications. Over-tightening or under-tightening can both lead to problems. Periodically inspect the terminal lugs for signs of corrosion, damage, or loose connections. If any problems are found, correct them immediately. Regular maintenance can help prevent electrical failures and ensure the continued safe operation of the equipment. Also, consider the available fault current at the location. High fault current requires higher interrupting ratings for the transfer switch and associated breakers, as well as appropriately sized conductors and grounding. The available fault current should be determined by a qualified electrical engineer. Coordination studies are essential to ensure that overcurrent protective devices such as fuses and circuit breakers operate in a coordinated manner to minimize the extent of any outage during a fault. For example, a downstream fault should cause only the closest upstream protective device to trip, leaving the rest of the system operating. Without proper coordination, a fault could cause a widespread outage. Grounding is another critical aspect of electrical safety. The grounding system provides a low impedance path for fault current to flow back to the source, which helps to quickly trip overcurrent protected devices and minimize the risk of electric shock. Ensure that the grounding system is properly installed and maintained in accordance with the NEC. Surge protection is also important, especially in areas prone to lightning strikes or voltage surges. Surge protective devices, or SPDs, can help protect sensitive electronic equipment from damage caused by surges. Install SPD at the service entrance and at downstream locations as needed. Arc flash hazard should also be considered. Arc flash is a dangerous phenomenon that can occur when there is a short circuit in electrical equipment. The intense heat and pressure from an arc flash can cause serious injuries or even death. Conduct an arc flash hazard analysis to determine the potential arc flash hazards in the workplace and implement appropriate safety measures, such as wearing personal protective equipment, or PPE, and using remote racking devices. Training is essential for all personnel who work on or near electrical equipment. Employees should be trained on the hazards of electricity, the proper use of PPE, and safe work practices. Regular refresher training is also important to keep employees up to date on the latest safety procedures. Lockout/tagout procedures should be followed whenever electrical equipment is being worked on. Lockout/tagout ensures that the equipment is de-energized and cannot be accidentally energized while work is being performed. Clearly label all electrical equipment with appropriate warnings and identification. This helps to ensure that workers are aware of the potential hazards and can easily identify the equipment. Regular inspections of electrical equipment can help identify potential problems before they lead to failures or accidents. Inspections should be performed by qualified personnel and should include a visual inspection, as well as electrical testing. Documentation is essential for maintaining a safe and reliable electrical system. Keep accurate records of all electrical work, including inspections, repairs, and modifications. This documentation can be valuable for troubleshooting problems and ensuring compliance with regulations. Remember that electrical safety is everyone's responsibility. By following safe work practices and staying up to date on the latest codes and standards, you can help prevent electrical accidents and create a safe working environment. When dealing with automatic transfer switches, consider the different types of switches available, such as open transition, closed transition, and soft load transfer switches. Each type has its own advantages and disadvantages, depending on the specific application. Open transition switches briefly interrupt power during the transfer, while closed transition switches momentarily parallel the two sources. Soft load transfer switches gradually transfer the load from one source to the other. The choice of switch depends on the sensitivity of the load and the need for uninterrupted power. Consider the reliability of the power sources being used. If one source is unreliable, it's important to have a backup source that is capable of providing power when needed. Regular testing of the automatic transfer switch is essential to ensure that it will operate properly when needed. Testing should include simulating a power outage and verifying that the switch transfers to the backup source. The control system for the automatic transfer switch should be carefully designed to ensure that the switch operates properly under all conditions. The control system should include features such as voltage monitoring, frequency monitoring, and phase synchronization. The enclosure for the automatic transfer switch should be properly sized and ventilated to prevent overheating. The enclosure should also be protected from the elements such as rain and snow. Proper labeling of the automatic transfer switch is essential for ensuring that workers can easily identify the switch and understand its function. The labeling should include information such as the voltage, current, and phase of the switch. The automatic transfer switch should be installed in a location that is easily accessible for maintenance and repair. The location should also be free from obstructions and hazards. Regular maintenance of the automatic transfer switch is essential for ensuring its continued safe and reliable operation. Maintenance should include inspecting the switch for signs of wear and tear, lubricating moving parts, and testing the control system. A qualified electrician should perform all maintenance and repair work on the automatic transfer switch. Ensure compliance with all applicable codes and standards when installing and maintaining the automatic transfer switch. This includes the NEC, as well as any local codes and regulations. The selection of an automatic transfer switch should be based on a thorough understanding of the application requirements. This includes the load size, voltage, frequency, and criticality. Consult with a qualified electrical engineer to ensure that the proper switch is selected. The installation of an automatic transfer switch should be performed by a qualified electrician in accordance with the manufacturer's instructions and all applicable codes and standards. After the installation of an automatic transfer switch, it should be thoroughly tested to ensure that it is operating properly. This testing should include simulating a power outage and verifying that the switch transfers to the backup source. Regular inspections of the automatic transfer switch should be performed to identify any potential problems. These inspections should be performed by a qualified electrician. Any problems identified during inspections should be promptly corrected by a qualified electrician. Proper documentation of all work performed on the automatic transfer switch is essential for ensuring its continued safe and reliable operation. This documentation should include the date of the work, the name of the person who performed the work, and a description of the work performed. Remember, safety is paramount when working with electrical equipment. Always follow safe work practices and consult with a qualified electrician if you have any questions.